Hello, welcome to this first feedback video of the MOOC. It was very nice to see you all on the forum and all the active participation. In week 0, I saw that you really were from all over the world. People from the US, from Europe, France, Germany, from Asia, people from India, Bangladesh, from Australia, South America, Brazil, and people from Africa. So we really have the whole world, all continents, active on our forum. It's very nice to see. And I also saw already in week 1 some people who did a lot of assignments. I was, for example, impressed by the C++ program to calculate the international standard atmosphere. Very well done. And there were also some questions. I will try to discuss them in this short video. The first one was about the fact that when we asked you to recognize different expertise areas, different departments, different areas of aerospace, that you commented that not all the pictures were also given in the lecture. And this is true, but this is on purpose. The idea was that you try to think yourself which connects with which, and that you try to deduce that for yourself. We will do that more often in later lectures. We might ask things that are really outside the actual lecture and which invite you to really explore for yourself. There were also some questions on the aerostatic equation and units and some of the balloons. To explain that, I need a blackboard. So let's go to one of the lecture rooms in this faculty and deal with those questions. The next question was about the disk of air that we discussed when we started talking about the atmosphere, the aerostatic or hydrostatic equation. There I drew a disk of air where I said there was the pressure P on the side underneath of the disk. We had P, and on the top side there was the pressure P plus dP, or initially it was delta P if we talk about larger steps. And some of you remarked, isn't that strange? Because when you get higher, the pressure should get less, which is true, but the fact that we chose the altitude in this direction positive, and means the delta altitude, or DH, also positive in this direction, that's why we also chose our dP, our delta P, positive in the upward direction. And of course it's true that the pressure will get less, but that simply means that the dP will be smaller than 0. And indeed, in the final result, we saw that the pressure dP was minus rho g dH. And because these are all positive numbers, we can here see that indeed the pressure becomes less when you go higher in the atmosphere. So in general, this means that if you draw a picture and you draw forces or anything in a certain direction, that doesn't have to be the right direction yet, but if you consistently use it in the same direction, then your result will simply get a minus sign when it has to be in the opposite direction. Another question was about the people getting stuck by calculating the temperature of a hot air balloon, which was required to give it the same lift as a helium balloon of the same volume. Well, if we look at the equation, I'm going to move a bit to the side here. If we look at the equation for the lift equation for hot air, and we say we want the same lift for helium, we can write the equation for both, the lift equation for both types of balloons. So rho Vg times, and we derive this equation for hot air. Rho is the atmospheric density times the volume of the balloon times the gravity acceleration times the ratio of the temperature increase divided by the temperature plus the temperature increase. This is basically the temperature inside the balloon. This has to be equal to the helium balloon, where it's again the rho of the atmosphere times volume times G times 1 minus the molar mass of helium divided by the molar mass of air. Well, we see that this part is the same. So you basically have to compare this with this. This we can calculate using the molar mass in grams per mole or kilograms per mole. In this case, it doesn't really matter because you use the ratio, but by default, it's always better to use SI units. So to immediately transfer them into the kilogram per mole. We often give gram per mole because that's a nicer number. And we will later see that with another number as well. But so this we can calculate because this is 4.00 and this is 28.97 and this is gram per mole. Gram per mole. Like I said, we can use this, but if you do it correctly, you should use these numbers, of course, for kilogram per mole. And here again for kilogram per mole. If you then calculate this, this is a fixed number. I think it's something like 0.862, which has to be equal to this. Well, this is also about, on average, I say it's about 6/7. In other words, 6 divided by 1 plus 6, and then you're already very close to finding out what the temperature inside the balloon needs to be to get the same amount of lift as when it's helium. You'll be surprised by how hot it is, and you can also see then that helium is much better at generating lift than hot air. So if we move to the other side of the board, there was one more question, and that had to do with the challenge. The challenge was basically about getting your own payload up in the air to make pictures of the edge of the atmosphere, because with a helium balloon you can get really, really high. And I would really love to see your video footage of that, your results or photos of high in the atmosphere using maybe an old camera, an old cell phone and some GPS to find it back. And see that, because we have students who have done it here. I've seen many of them, and it's really, really a very nice way to make pictures like they're from out of space. And some of you were concerned about my iPhone. Well, and you could calculate whether it's, I invited you to calculate that. And basically, the idea is that you can calculate the lift generated by these party balloons. The ones that we use were standard party balloons, and the volume of a standard party balloon is between 11 or 14 liters. Let's be optimistic and use the 14 liters, which means that our volume of the helium balloons, in total we have 4 balloons times 0.014 cubic meter, which is 0.056 cubic meter of helium maximum. Well, the lift equation is atmospheric density times volume times G times 1 minus the molar masses. And if we use the standard atmosphere here as a guess 1.225 kilogram per cubic meter, and we fill this in, we get for the 4 balloons that the lift is 0.5798 Newton, which means the payload has to be the lift divided by G, as the gravity force is m times G. And this means that the actual lift capability is 0.059 something kilogram. In other words, around 59 grams is what these 4 balloons could lift. The iPhone is of the type iPhone 4. iPhone 4, and it weighs 132 grams. So 4 balloons cannot carry a 132 grams iPhone. So don't worry, I still have my iPhone with me. It's okay. And if I wanted to use my iPhone and really lift it with the balloons, then you can calculate with this that I would need around 8.95 balloons in other words, probably 9 balloons would at least be needed to lift my iPhone. And you could see in the video that I only used 4, so that the payload was not my iPhone. So, thank you for your concerns, but I still have my iPhone, and don't worry about that. And I would be really pleased if you can send me some footage of your payload underneath these balloons. Well, good luck with the other exercises and the lectures. We're going to go really fast. It's not always easy. So keep up the good work and try to keep trying with those exercises. And I'll see you again in the next video.